Hi everyone, welcome back to class. Before we start the class today, there are a few announcements. So basically, assignment 3, the deadline has passed, and the TA is going to graduate the assignment soon. The first announcement is that basically after we finish assignment 3, then we are going to assignment 4. So assignment 4 will actually be posted tonight, uploaded to the course website. And I will send, as usual, I will send an email after we post it to our course website. And the deadline is still going to be within 2 weeks. The deadline is going to be basically 3 p.m. Tuesday, November 15th. Yeah. This is going to be announcement for assignment 4 here. So the second announcement is actually for the project proposals. So the TS has replied the emails for the feedbacks. So basically, I think in general, I think all of you are doing a good job, and I think we are really looking forward to see your final report. If there are some suggestions or comments, I think we basically left that in the email. But in general, please keep up your good work here. The third announcement is that basically, after we have finished the project proposal, we are actually also moving to the final report. So actually, some of the students asked about like the template for the final report, and actually the template for the final report will also be posted tonight. So it will actually be posted together with assignment 4 here. As a reminder, the deadline for the final report will be the end of week 14, which is going to be December 11th, at the end of the day. Okay, so those are basically 3 quick announcements. So if there are any question here. Okay, so if there is no question about the announcements, let's go into our the technical things that we are going to introduce today. So basically today we are going to introduce network flow algorithms. So in general, throughout this class, we have been really seeing a lot of different kind of examples. So going through many instances. So basically, we have been seeing 3 different kinds of algorithm design ideas. So that is basically a greedy, divide and conquer. And also dynamic programming. So those are like 3 basic algorithm design ideas. So today we are going to introduce, I think, basically the last general class of algorithm design ideas. So basically today we are going to introduce the last class of ideas. So the name of this kind of idea is called a network flow. So you can probably see from the name, in general, talking about like greedy, like divide and conquer, and dynamic programming. Those sounds like very general words, talking about some general kind of thoughts. So network flow, from the name, I think it is actually a little bit specific. It's actually talking about networks and actually talk about like flow on networks. So maybe, I'm not sure, like in general, from a first look, like network flow is like comparable to greedy, divide and conquer, and dynamic programming, whether it is actually a little bit specific. But I think if it turns out that actually for the lecture today, we will actually mainly introduce algorithm for the network flow problem itself. But actually for the next class, we will see that the network flow algorithm actually has a lot of applications. Maybe some problem at the very beginning is probably not like a network flow problem, but actually it can be regarded as a network flow problem and can be actually solved very efficiently. So I think according to this name for the network flow algorithms, I think basically as I just mentioned, the plan today is that we are actually first going to introduce what is a network flow and basically what are the good algorithms for the network flow problem. So of course, I guess in general, definitely it is actually originated from graphs. And actually, we definitely need to first introduce what is the definition of the network flow problem. Okay. So the first definition that we are going to give is the flow network. So for flow network, so we are basically going to consider a graph, a T, which is having a vertex set V and also edge set E. And actually, for the flow network, because this really sounds there are some directions inside. So in general, we consider a graph, and here we consider directed graph. And I guess for our convenience, we just say that the graph is actually simple. By simple, it just means that the graph has no parallel edges. So basically, it does not have the case where there are like two edges. So we assume that there are no parallel edges, and actually also no self loops to make everything look simple here. So for the flow network, it is not only a directed graph, but also we have two vertices. So we actually mark them specifically. So we say that there are actually two distinguished nodes. So basically, one node we call it as S, which is a source, and we have like a T, which is a sink. Excuse me. So this T also comes from the English word terminal. So which is like the end that we actually want for. So actually, we also have the further assumption that S actually only has out edges. And actually T only has in edges. So I guess for our convenience, I guess we also assume that all nodes have at least one edge. I mean, in or out. I mean, no matter it is in or out. I mean, if there is a node that does not have an edge, I mean, based on our discussion, it is not hard to see that we can just ignore that vertex or node. So basically, the vertex and node means the same thing. I mean, throughout the stuff. Yeah. So basically, without loss of generality, we just for our convenience, we assume that all nodes actually have at least one edge here. Basically, this actually ensures that the M here, the number of edges is basically at least n over 2. Then where n is the number of vertices. And actually, this is assumption that we are going to use throughout the discussion today. So I guess this is still, I mean, just like a mathematical definition here. So maybe let's actually see an example here. So let's maybe, for instance, take a look at this graph. So assume that here we have like an S. And so maybe assume that we have a few different nodes in this graph. So S is currently here. Maybe assume that maybe we have like a 2. We have, let me write this a little bit larger, like a 2, like a 3, like a 4 here. So actually assume that we have this kind of edges here. And actually maybe, I mean, assume that maybe there are some other nodes here. So here maybe there is a T. So let's, for instance, let's consider a graph like this. So there can be like several edges among them. So maybe let me actually a little bit here. So for instance, I mean, maybe based on this discussion, we assume that S only has out edges and T only has in edges. So let's basically assume that the edge directions are actually looking like this. But actually, the edge directions in the middle can be a little bit, I mean, it can be a little bit arbitrary. So for instance, maybe we consider such kind of edges. So let's, for instance, consider a graph like this. So basically for this graph, I mean, in general, I mean, this is a directed graph. And actually, very importantly, I mean, in general, for the network flow, basically a flow network, we can also have the further definition that this graph is not only directed, but also on the other hand, it is weighted. That actually we can put weights on the graph. So basically, we consider like capacity. So basically, we have the definition called a C of E here. So this E is basically taken from some an arbitrary edge from the graph. So we have like a function C here to represent the capacity of E. So in general, we can consider a weighted graph. And for instance, assume that maybe we have a graph like this. Maybe we can have a corresponding some weights on those edges. So for instance, maybe there's like a 10, like a 5, like a 15 here. Maybe let me just write something down here. So those are like correspondingly the weights of the edges. So basically all these numbers I'm writing here are like the capacity of the capacity of each of the edge. Okay, so is there any question about like the definition of the flow network here? Okay, I guess this should be a relatively straightforward. I mean, basically we have a directed graph, and furthermore, we are actually considering a weighted directed graph here. And basically we have direction of edges here, and S only has out edges, T only has in edges, basically following the definition here. So I guess this is basically a very first definition. Maybe we can consider some further definitions here. And basically we want to, in general, consider something interesting on this kind of directed graphs. So basically we have a definition. So we have a definition for an ST cut. So an ST cut is basically a partition of V. Basically the V here is the vertex set. So a partition of E, I mean into two disjoint sets, A and B, where S and T actually they are in a different set. So assume that S is in A and T is in B. And following this definition, and basically we can define like a cut for the vertex set. And basically following this, I mean, we want to evaluate, I mean, what is like, I mean, somehow it's like, what is the performance of each kind of the partition here? So basically we can have like a following definition according to this. So the definition here we are going to use is that the capacity of a cut AB is actually defined as cap. AB equals to the summation of all the edges out of A and with their capacity. So here, I think I need like a further explanation about like what is E out of A here. I mean, if it is out of A, it is basically supposedly to saying that an edge, I mean, starting from A and actually ends in B. So basically there can be, I mean, 4 kinds of edges. I mean, like an edge, I mean, start from A and go to A, start from A, go to B, start from B, go to A, and start from B, go to B. So basically we here consider all the edges starting from A and go to B. So I guess maybe we can actually see an example along this. So I guess maybe for our convenience, I think basically in the discussion, let's try to use a graph again to basically make sure that we have a good understanding about like what is actually the definition of the ST cut and the capacity here. So here, I mean, in general, we have a lot of different ways to basically partition the vertex set. I mean, this is basically later on we want to figure out like a better way. I mean, in general, like a good way that maybe we want to consider some kind of the good cuts, basically. I won't say a good cut, but basically some cuts that is needed that basically satisfies what we actually want here. So let's, for instance, consider the case. I mean, basically, assume the case where this is A here. And basically the rest is B here. I mean, basically for our convenience, we just don't write everything down, but then just imagine that, I mean, a vertex, if it is not in A, it's just in B here. So I guess maybe a first thing that we can try is that we consider set A here to contain only the vertex S here. So in this case, what is the capacity of the graph? Yes, so here in this case, the capacity is 30 because it is only just 10 plus 5 plus 15 equals to 30. I guess this should be a relatively straightforward. And I guess maybe we can take a look at another example. So maybe, for instance, here we consider a larger graph. I mean, maybe we can consider something like this. So maybe let's consider this. So let's assume this to be the A here. So what is the capacity of this partition? So here we want to be a little bit careful because actually, I mean, for instance, like this is an out edge, and actually this is also an out edge. But actually, in this case, there are some in edges here, like this. According to our definition here, we actually don't worry much about the out edges. So sorry, the in edges here to A here. We only want to take the summation of all the E actually out of A here. So basically, the capacity of this partition is actually going to be 9 plus 15 plus the 8. So 8 is basically for this edge. And I guess we just need to ignore the edge with 6 here. And actually, finally, plus 30 goes to 62. Okay, so any question about this definition of the ST cut is corresponding capacity? Okay, so if there is no question, I guess this basically goes to the first question that we are going to think about. I mean, in general, maybe we can see that, for instance, treating this as the set A here, I mean, the capacity here is 30. I mean, for the later part, I mean, this sounds like, I mean, this partition, I mean, intuitively, it is probably not as good as the first one. I mean, it also depends on what is our goal here. I mean, in general, our goal here is actually we want to seek for the cut actually has the smallest capacity as possible. And actually, because we are looking for the smallest capacity, I mean, in general, according to cuts, and this is typically called the minimal cut problem. So for this minimal cut problem, the goal is just to find an ST cut of a minimum capacity. So basically, this is the first problem that we are actually going to implement. So let's maybe, for instance, think about actually take a look at this graph. So maybe, I mean, for instance, I mean, taking the set A here to be the S, I mean, that actually sounds quite good. I mean, the capacity 30 here is actually much smaller than the 62 here. But it's actually, this is the minimum, is actually this the minimal cut. I mean, let's take a close look at this example. I mean, for instance, is there like a more clever way for you to do this such that maybe the value of the cut is actually small? Nine, 10, 10. So which vertices are you taking for the set A here?
S 2, 3, 4, 6, 7.
I see. So let's actually take a look at that. So you are suggesting that we can probably take this. Right, let's take a look at this. So basically for this subgraph, we are actually having out edges. I mean, we actually have this is an out edge, and this is actually an out edge. This is actually an out. So basically, indeed, so the capacity for this subgraph is actually equals to 9 plus 10 plus 10 equal 29. But actually, I'm actually maybe I'm a little bit more clever than you that actually I can even find like a cut with smaller capacity here. So let's, for instance, consider this set. Let's, for instance, consider this set. So for this subset, what is its corresponding capacity here? Yes. So we have this actually, this is the out edge here. I mean, this first is an in edge, so we don't need to worry about that. But actually, this is also another out edge, and actually, this is another out edge. So basically the capacity of this cut is basically 10 plus 8 plus 10, actually 28. And actually, I mean, since we only have like a constant number of nodes, I mean, we only have 8 nodes here. We can just, I mean, brute forcefully check what is the optimal capacity here. And actually, this is you can later check this by yourself, but actually this is optimal for this current instance. So basically, this is a definition of the minimum cut. So is there any question about the definition? Okay, so I mean, if we don't have any question, I guess it's probably the time that we want to think about. I mean, what is a good algorithm for this? I mean, in general, I mean, for graphs, I mean, we talk about a lot about like different strategies. I mean, like greedy, like basically, and I guess for a lot of graph problem, also we can do that by dynamic programs. So for instance, basically, last time we talked about this Bellman-Ford algorithm for solving the shortest path problem, even with negative weights. So basically, I mean, for this network flow problem, we are actually also going to use some of the algorithm design strategy here. But I guess to do that, I mean, I guess basically for the lecture today, we have some sort of definitions here. But actually, let's first basically list all the definitions and then figure out what are the problems that we can actually solve here. So here, I mean, basically in general, I mean, according to the to like the topic today that we talk about network flows. But here it's basically, I mean, first having a graph here, it is very natural that we want to consider like maybe you want to cut a graph, etc. But what is like the notion of having a flow here? I mean, basically we need to also characterize what is like a flow. So for instance, I mean, basically maybe you can consider some kind of like ST paths here that basically we want to maybe, for instance, have something that is actually flowed from S to T here. So that is actually also something quite intuitive here. And maybe you want to actually grasp such kind of a notion that in general, maybe for a weighted graph here that we can have some kind of flow that basically maybe some value that goes from S to T here. And in general, we just consider some flows, maybe for instance, like an air flow and basically like a water flow. It is basically something consecutive that you have this kind of amount move from the one place to the other place. So that is basically the notion of a flow. And according to this, we can have like a similar definition of flows and graphs. So basically a definition that we are actually having here is that after defining the mean cut problem, we are actually also going to define a flow problem. So we say that ST flow is basically a function f that satisfies actually for each edge E here, we actually are going to have this function value actually 0 smaller than FE, smaller than the capacity C of E here. So this is basically a constraint called a capacity constraint. So it's basically, I mean, in general, consider some kind of flows. I mean, you always have like a large amount here. I mean, the largest amount that you can make the flow maybe in one from one place to another. So basically, in this case, it's basically like the weight here on this on the edges of the graph. There are just like the capacity constraints that we need to follow for each of the edges here. So the second point that we actually are going to make is here is that for each vertex, V, that is not S or T here, we have the summation of E into V, Fe, equals to the summation of E out of V, Fe here. Let me actually move this a little bit further here. And this is actually called a conservation constraint. I guess intuitively you can maybe think this actually it makes a lot of sense because we want to talk about in general a flow problem from S to T here. So you don't want to maybe, for instance, like get stuck in the middle. I mean, in general, maybe you don't want to lose some values here. You just want to consider that the flow that actually move from S to T and basically in the middle, it is also always actually always conserved in the sense that the summation of the flow into a certain vertex V that is not equals to S or T equals to the number of flows out of the corresponding vertex here. So this is actually a relatively a natural definition from my perspective. And I guess actually maybe we can also think about, we just continue to use this example here. And maybe we can think about what is like a flow here. So maybe let's just consider like a flow. Maybe we want to take this path, from S to 2, 2 to 3, 3 to 6, and maybe 6 to T here. So we can maybe, for instance, consider a flow along this line. The really like the bottleneck here is basically the edge from 2 to 3 here. Yeah, because actually the capacity, from S to 2, 10, the capacity from 2 to 3, which is 4, 3 to 6, which is 8, and actually the capacity from 6 to T, which is 10. Among those, the capacity of 2 to 3 is actually the lowest. So nevertheless, I guess if we know what is this value here, well, actually the capacity here this word looks really weird. So basically for this flow, I guess the bottleneck here is actually going to be this 2 to 3 edge here. But nevertheless, let's maybe consider like the flow here where this value is 4, 4 here. At all the other edges, we can actually also all draw like this, but actually we just put 0 widths on all of the other edges. So basically we consider something like this. So basically the flow here, basically it is a flow according to our definition. And basically we need like a characterization about how good this is actually is. So basically this is probably not the best thing that we can do, but at least maybe for instance, we can also do something like this. So for instance, maybe we can actually consider another flow like this. And actually for this flow, the capacity here becomes the edge of 4 to 7 here. But nevertheless, maybe we can put like a 3, 3, 3 here. So basically, we can just do such kind of things. So basically, to characterize how good a flow is, basically the thing that we need to basically mainly concern is actually the amount that we actually remove from S to T here. So from this perspective, it is actually very natural to give a next definition. The value of a flow is actually just denoted as VF is actually just the summation of all E out of S. And here, basically, according to this definition, the flow, the value of the flow here is just actually 4 plus 3 equals 2, 7. So is there any question about this definition, basically the definition of flow and actually the value of this flow here? So here, maybe we actually also want to think about like further what is a good flow here. In general, from this perspective, maybe we want to put actually as much flow as possible from S to T here. So in general, like according to like such kind of notion here, in general, we want to have as much flow as possible. Then this is basically going to have the next definition. Basically the next problem that we are going to study today, which is called the maximum flow problem. So for the maximum flow problem, we just need to find ST flow of a maximum value. So basically throughout the lecture today, we will actually just focus on both problems, the minimum cut problem and also the maximum flow problem. And we are going to give a very thorough understanding about what is the algorithm for the minimum cut problem and also the maximum flow. So, okay, so I guess we have been keep talking about the same instance. So maybe let's take another look of this instance. Let me actually copy and paste this for another time. So actually, can you think of like a better flow? For instance, a flow maybe value is larger than 7. Can you think of like a better flow for this instance? So this is probably a little bit complicated. I mean, the value of flow is probably not as intuitive as the value of the minimum cut. But let's actually see such kind of flow here. So here, I mean, in general, we are going to put a width on a lot of edges. I mean, in this flow, actually, not a lot of edges have width 0 here. So let me just use the red color to represent the value that we actually are going to go through throughout the corresponding edges, basically the value of the f for all these edges. So let's consider such an example. So we are basically from S to 2, we have value 10 here. I'm actually just writing everything down here. So there's like a 4, 14, it's like a 0, 0, actually like a 9. And actually here we just use a 1 here. And actually we have a 0. And basically for this edge, we have an 8. And basically for this edge, we have a 4. And for this edge, we have a 14. It has like a 0 here, like a 9, 9, 10. So, I mean, what is the value of this? Sorry, we first probably need to check whether this is actually a flow or not. So basically, according to the definition of the flow here, we first need to satisfy the capacity constraint. But I guess the capacity constraint is relatively easy to verify because all the values that I wrote down for basically I wrote down in red, basically the value, the f value that we are going to use is actually smaller than or equal to the black values, that the capacity of all the edges. I guess this is probably relatively straightforward. I mean, when I'm actually writing down these numbers, actually I'm being very careful here that actually the number of the red colors I'm writing down is actually indeed smaller than or equal to the corresponding black colors. So the key thing here that we actually need to check is the conservation constraint. So let's actually maybe, for instance, do this by hand. I guess basically, for instance, in this vertex 2 here. So this is actually a conserved because we actually have an in edge, which is the value of the in edge. The value of the in edge is actually 10 here. The total out value, I mean, basically, there are 2 edges, one with value 9, the other with value of 1 here. So actually, we can see that this is indeed conserved. And I guess on the other hand, maybe we can also check maybe, for instance, the vertex 3 here. So vertex 3 here, actually the in edge here actually has 2 in edges. So we have like 4 here, and actually there is another 4 here. So there are actually 2 in edges, and the total value is actually 8. And actually, this is indeed correct because the total value of going out is actually also 8 here. So we also got a conservation for the vertex 3 here. So I guess I'm just probably not going to do this again and again. But in general, it can not very hard to verify that actually for the vertices, I mean, 2, 3, 4, 5, 6, 7, they're actually all conserved. So actually, this is good according to our definition of the flow here. And actually, it is also on the other hand, not very hard to check that the value of this flow is actually going to be 10 plus 4 plus 14. We are just actually looking at these numbers because according to the definition of a flow here, it is just the summation of all the edges going out of S here. So it is actually a 10 plus 4 plus 14 here equals to 28. So somehow there's, I mean, there's really like a coincidence here that the value of the, I mean, the max flow value of a graph actually here equals to the minimum cut value of a graph. So this is actually quite interesting. I mean, from this small example, we see that actually, I mean, you can actually check offline by yourself that actually this cut that we are actually given here, I mean, basically this cut, we are actually given here is the maximum cut here. And actually, you can also check offline. I mean, maybe you just think carefully about the instance I'm giving here. This is actually the max flow of a graph. So maybe this is probably suggesting that in general for such kind of network flow problem, maybe the maximum cut, the minimum cut problem is actually very connected to the maximum flow problem. Maybe their value, they are actually equal. So basically in this class, we are actually going to prove this, but actually proving this, we need some preparations. In general, we need to have a good understanding about like what is the intrinsic structure of the maximum flow problem and also the minimum cut. Okay, so any question about this definition of flows and basically like for this instance, like basically the flow here. Okay, So I think we will further, according to basically our discussion here, at least from this example, we see the connection between the the minimum cut and the maximum flow problem. So following this, first thing that maybe we want to argue here is a result called a flow value lemma. So what is the intuition here? The intuition here is that, in general, the original definition here that we are giving, for the value of a flow here is that we basically consider the sum of all the edges, E out of S here. But at least, for instance, you can actually also see this. We can actually replace this E out of S by E into T here. I guess you can clearly see the intuition because all the nodes in the middle, they are conserved. There is no, actually, the summation of all the weights here should just be 0. So the first thing that is actually quite intuitive is that we can clearly replace E out of S here by E into T here. But maybe there are actually also some other ways that we can make such kind of calculation here. And maybe we don't have to restrict to S and T here to calculate the flow value here. So the first thing that we actually are going to prove here is that we can let F be any flow. And actually, we also let AB be any ST cut. So then the flow the cut. So this is a little bit tricky. We say that the flow across the cut. I'm going to later figure out what this is, but we are just saying that this is actually equal to the amount leaving S. So where we say that the flow across the cut is that basically because we are having this kind of AB cut here. So in general, we can consider such kind of definition that we consider summation of E out of A of FE minus the summation of E into AFE equals to the summation of EF. So basically, intuitively, this is what we mean by the flow across the cut. Basically, typically, the tradition here that we are going to use here is that we always assume that S is in A and T is actually in B here. So we have this kind of cut A and B here. Then we can correspondingly define this kind of, this flow. Basically, we can regard this vertices, like a group in A and the other group in B here. And basically, we consider a summation of E out of A and E into A here. And basically, we actually I want to make sure that this summation, the difference of these two summations is actually always the value of EF here. So maybe let's actually, on the other hand, take a very quick look at the example here. For instance, let's consider this. Still, let's maybe consider this example. I guess I probably don't need to always copy this capacity. I guess it should be already relatively familiar to you. So, according to the original definition, let me actually use the blue color here. So according to the original definition, it is basically like regarding this S, this single vertex as the set A here. And basically here we get this value is just equals to 10 plus 4 plus 14, which is actually equals to 28 here. So, but how about maybe let's consider some other cuts here. So maybe, for instance, we can consider this cut. It is also okay that we regard this, as a 2, 3, 4 as the set A here. So we can also compute its corresponding value. So what is the value of this? Of this cut A here. So here we want to be careful because we also, we need to have like a plus sign for E out of A here. And also we have like a minus sign about like E into A here. And here you recall that we have the assumption that, basically, let me actually make a mark here, remark. So by our definition, S only has out edges. which just means the summation E into S FE just equals to 0 because there shouldn't exist such kind of edges. So the summation should just equals to 0. So we clearly see that if we take the mean according to this, if we take the A here just to be the set of single vertex S here, it just like follows the definition. But we furthermore here we really want that in general, I mean for arbitrary A here that the summation of E out of A FE minus the summation of E into A here of FE here is actually still equals to the value here. So I mean, continuing our example here, I mean, we can actually just feel free to consider maybe, for instance, basically this set A here. So basically for this set A here, I mean, the value here, we can actually make a calculation here. So the corresponding edges here is that basically, for instance, for such kind of edges, this edge is not like an edge E out of A here because it starts from A but also ends in A here. So this is not something we want to worry too much. So basically, we need to consider, for instance, like this edge, and actually also this edge, and actually also this edge, and actually also this edge. So they are actually the out edges, but actually there is an in edge here. So basically this edge. This is also an edge that we need to take care of. So basically, I mean, following the out edges, so here we are actually going to have 9 plus 1 plus 8 plus 14. And actually there is an in edge from 7 to 3 here. So we are actually going to minus 4 here. So a quick calculation here is that you can see that this actually also equals to 28. But actually this is the same as the value that we just like choose this set A here to be the set S here. So this is just like a showcase about like, I mean, the correctness of this flow value lemma. But of course, here I'm actually going to give you a formal proof for this. So this is just like an intuition on this. And actually, let's just do that to a proof. So again, a very important thing is that, I mean, a main difference, I mean, from the set that only has the vertex S to be the set A here, and actually maybe some arbitrary A here, is that basically in general, maybe we want to utilize the fact that actually the vertices in the middle, like 2, 3, 4, they're actually conserved. So actually they don't actually bring into additional flow values. So this is basically a key observation that we are going to use here, that actually by flow conservation. And actually, we know that the summation of E into V FE actually equals to summation E out of V for each V actually for which each V that has in A but not equal to S. And actually, we note that actually T is actually always in B, so T is actually not in A here. So the V here, I mean, if you pick like a V for each V in A, I mean in A, but it's not S. I mean, this of course, you are not going to be able to pick T here because T is actually already in set B here. It actually does not even in the set A here. So this is basically a place that we need to be a little bit careful here. So therefore, we can see that the value of VF, I mean, just according to the definition of VF here is actually equals to the summation of E out of S Fs. And then actually we can take a further summation among all the vertices in A here. So summation of V in A, summation E out of V or Fe minus the summation E into V Fe. So this is correct because only when, I mean, we just make a comment, only when V equals to S, and this is non-zero. So, I mean, in general, we consider this summation here. I mean, actually, among this summation, I mean, we take the summation of all the V in A here. I mean, actually, when V does not equal to S, basically this value is just 0. And when V equals to S, I mean, it's just this, right? As we just discussed, the summation of E into S is actually just 0 here. So this is basically something quite intuitive, I guess. And basically, it is a main reason why we can mean for this definition of the flow value, we can go from like a single vertex S to some arbitrarily partition, basically the arbitrary set A here. And actually, after doing that, we need to actually also clear the summation terms here. So we articulate a summation of all the V in A here, and we want to study the address E out of A here. So we just make the claim that this just equals to what we want here. Actually, this just equals to E out of A, Fe, minus the summation of E into A here. Actually, this is problem solved. So why is the last equality here true here? So we just like consider, I mean, like an arbitrary edge here. I mean, basically, if one edge, one of the end is actually in A here. So let's say that belongs to A. So the point is that basically, if we consider all such kind of edges, I mean, basically the starting edge is actually already in A here. So if it is actually already, I mean, the other vertex, I mean, the vertex it reaches is actually also in A here. So actually, we know that the edges in A, into A and out of A, they just cancel. I mean, because basically, if you have a vertex here, and actually it is if it's taken in the sum. And if on the other hand, you know that actually this vertex is actually belongs to A here, you actually got another Fe here in this minus E into A here. So it just actually got canceled here. But nevertheless, I mean, if you have this case, I mean, if you start from a vertex in A here, but actually you reach a vertex in B here, this is actually exactly the definition of E out of A here. And basically in this definition, you can clearly see that basically this Fe is actually you actually calculate this value. I mean, you have like a plus value basically in this summation. And because you are not talking about the B here, so basically you don't take out anything here. So you actually just like save the value Fe here and actually making this into the sum. And actually this is exactly what we mean that basically we take the summation of E out of A here. So basically, oh, excuse me. I mean, we just say this is present in the sum. And actually, this just finished the proof of our flow value lemma here. But in general, whenever we want to talk about the flow value of a certain flow here, I mean, we don't always need to take a look at the value only at the vertex S here, but an arbitrary cut here. I mean, for our arbitrary A here, it is fine that we just consider the value of E, the summation of Fe for all the E out of A minus the value of E into A here, and we can basically calculate the flow value here. Okay, so any question about this flow value lemma, basically about the proof? Okay, so I guess I have like around 2 minutes for this first class. I mean, basically for the first hour. And I guess maybe let's make a further definition here. Then let's take a break here. So in general, I mean, we want to, I mean, based on this intuition, basically based on this instance that we are looking here, we want to have some sort of connection between the flow values and also the cuts. And basically this flow value lemma is like a very first step that we are actually making along this line. So basically another thing that we can actually again notice here is called a weak duality. Oh, excuse me. So what is the weak duality here? So this is actually such kind of fact. So basically we consider like any flow F. And actually, I mean, as we just have been doing, we can consider any ST cut here. So we say then the value of the flow is actually at most the capacity of the cut. So this is basically saying that, okay, for instance, I mean, one of the students actually gave an example here. So one of the students gave an example here. So okay, here for this flow, we have this a choice of the cup and the corresponding capacity value equals to 29 here. And then basically this directly implies that the flow value is smaller than 29 by the weak duality lemma here. So basically, this is an intuition about like why we want to have such kind of lemma here. And basically, in the next hour, we are going to prove this weak duality and also for the definitions and algorithms here. Okay, let's take a break.